Hi, my name is Seth, and in this video, I will discuss a machine theory of mind approach to agent intervention. Before getting into this work, it is key to understand that theory of mind refers to the ability to understand others' internal mental states. False beliefs can be first order, which occur when a player has a different belief about their environment than what is true, or second order, when an agent has a different belief about the player's internal states than what is true. An intervention is an instruction to a human player that helps them correct their behavior while performing a task suboptimally. Reinforcement learning models in this work rely on mental state, using an LSTM's memory cell to represent internal states. Curriculum reinforcement learning trains agents on a series of more complex challenges in the hope that the agent is able to learn the new task with the previous learned experience. In this paper, we take two parallel approaches to solve the intervention problem. First, we identify human first-order false beliefs and use them to analyze intervention scenarios, which can be classified from human data. Next, we use curriculum-based reinforcement learning to train an expert agent on the task. The learned value function can be used to determine when an intervention is necessary. That is, the value function acts as a second-order belief predictor of the human player's action policy. Agent interventions in human behavior will be determined based on the theory of mind state. This figure shows our theory of mind model in action. The theory of mind consists of players' internal states, such as intention, cognitive state, and player belief state. The representation of this is inputted to the intervention network to decide whether an intervention is necessary. To determine human motivations for search and rescue, we collected human data searching and triaging victims in Minecraft while thinking aloud to show their strategy. On the left, we can see an image of a player triaging a yellow victim with a green victim in the background. The player is also given a blueprint of the environment before the disaster struck. Human observation data shows a series of fixed searching strategies based on the triaging strategy. The decisions in the previous graphic may lead to suboptimal behavior, especially when players' internal states are challenged. They often lead to false beliefs, creating an intervention scenario. With respect to triaging interventions, while different triaging strategies may be optimal, all strategies can lead to suboptimal situations. For example, in a greedy strategy, where players triage all the victims in the vicinity, players may miss victims, requiring an intervention. With respect to terrain interventions, changes in terrain require deviation from intended trajectories. Interventions can help the player adapt to a new optimal trajectory. Memory interventions are required to reduce redundant searching. Memory-intensive strategies, such as second sweep, where one triages all high-risk victims before triaging any others, are riskier without intervention. For example, if the player is forgetful and does not remember the correct location of victims, intervention is necessary. In the second direction of this work, the minigrid representation is extracted from Minecraft to solve a simpler learning task. Environments range from simple to complex to one that is difficult for humans, providing a challenging curriculum-based learning problem. These are images of sample environments, but intermediate difficulties exist between them. During training, we see that the value function diminishes as the agent is trained in more challenging environments, and so ultimately not being able to complete the task in the human difficulty environment. The value loss output concludes the same result. Training is successful until the environment complexity is too great. The maximum reward return shows that optimal performance can occur in most environments. The mean reward output yields favorable results for most environments on average. The reward minimum return yields a lower bound on the good performance in the first three environments. The reward standard deviation shows that beginning training in new environments is more difficult as the complexity increases. The issue with training in larger environments is that the reward signal is sparse. In future work, this will be addressed by adding short-term rewards for intermediate goals. I thank the National Science Foundation and Carnegie Mellon Robotics Institute for making this work possible. I also thank all Robotic Institute Summer Scholar sponsors for making this program possible.